Here's something that should genuinely blow your mind. Right now, as you sit there watching this, you are hurtling through space in multiple directions at once. The planet beneath you is spinning on its axis, carrying you at up to 1,600 kilometers per hour, depending on where you live on Earth. At the same time, Earth itself is orbiting the Sun. The Sun is cruising through the Milky Way. The Milky Way is moving through what we call the local group of galaxies. And the local group is moving through our local supercluster. And even that entire supercluster, an almost incomprehensibly vast collection of galaxies, is itself in motion, being drawn towards something called the Shapley Supercluster, where scientists believe there is an extraordinarily large concentration of galaxies packed together. Now, to understand why any of that is happening, we need to take a step back and talk about the big picture of how the universe is put together, and about a force that quietly shapes everything. If you've been keeping up with our recent episodes, you'll know we've spent some time talking about the large-scale structure of the universe. Galaxies aren't scattered randomly through space like confetti. They're organized into enormous filaments, long, thread-like chains that form a kind of cosmic web. And in between those filaments, vast empty bubbles called voids, where almost nothing exists for hundreds of millions of light-years in any direction. The universe is expanding, which means on the grandest scales, everything is moving away from everything else. Think of it like dots drawn on a balloon being slowly inflated. The dots don't move on their own, but the surface stretching between them pushes them apart. But here's the thing, that's not the whole story, because there's another force at play, one that works in the opposite direction. That force is gravity. Gravity is, at its most fundamental level, the curvature of space-time caused by the uneven distribution of mass. Wherever you have mass, you have a dent in space-time, and other masses roll toward that dent like a marble rolling toward the center of a curved bowl. On very small scales, gravity is almost irrelevant. You don't feel yourself being pulled toward the chair next to you or the building across the street. But you absolutely feel the pull of the Earth beneath you because the Earth is enormously massive. On larger scales, planets are dominated by the gravity of their star, and all the stars in the Milky Way orbit around the supermassive black hole at its center. But gravity doesn't stop there. It operates on scales almost too large to imagine, which might sound strange. If everything is moving apart, how can a whole galaxy be moving toward us? The answer is gravity. When objects are close enough together and massive enough, gravity pulls them toward each other faster than the universe's expansion can push them apart. This is why we have galaxy clusters and superclusters. Gravity wins the local tug-of-war against expansion, keeping these enormous groupings of galaxies bound together. And that means, over extremely long timescales, galactic collisions aren't some rare, unthinkable catastrophe. They're actually not that unusual. In fact, there's a fascinating new theory suggesting that the Milky Way itself may have recently experienced exactly that kind of collision. Scientists have proposed that our galaxy collided with a large, diffuse galaxy, roughly the size of the Large Magellanic Cloud, called Antlia Two. The evidence? Ripples. Scientists discovered that the disk of the Milky Way has wave-like ripples running through it, consistent with having been disturbed by a major collision sometime in the past. But for a long time, they couldn't figure out what we'd collided with. Then the Gaia Space Observatory, a European Space Agency mission designed to map the galaxy in extraordinary detail, discovered Antlia Two lurking behind our own galactic disk. And that location explains everything. Hidden behind the dense band of stars and dust that makes up the plane of our galaxy, Antlia Two is incredibly hard to spot. It's a massive galaxy, but it's spread out over an enormous area, most likely a consequence of the collision itself, and the galactic disk sitting in front of it blocks our view like a fog bank obscuring a city skyline. So galactic collisions are real, gravity is powerful, and structures in the universe can hide from us in plain sight. Which brings us to the main event of this episode, something that is, frankly, one of the most mysterious and awe-inspiring features of the cosmos we know of. Something called the Great Attractor. If supervoids are the universe's empty deserts, regions where there is almost no mass for hundreds of millions of light-years in any direction, then the Great Attractor is the opposite extreme. It is the greatest concentration of mass for hundreds of millions of light-years around. And we mean that literally. Our galaxy, the Milky Way, is somewhere between 150 million and 250 million light-years away from it. And yet, despite that enormous distance, we and every galaxy in our neighborhood are being pulled toward it, right now. All of us, moving inexorably in the same direction, drawn by this invisible gravitational titan. Estimates put the mass of the Great Attractor at roughly 1,000 trillion times the mass of our Sun. Let that sink in for a moment. 1,000 trillion solar masses. That's enough mass to account for many thousands of entire galaxies. So what on Earth, or rather, what in the universe, could possibly be sitting there? For a very long time, nobody knew. The Great Attractor was one of astronomy's most maddening mysteries, not because we lacked the intelligence to understand it, but because we literally couldn't see it. Just like Antlia Two, the Great Attractor sits in a direction that is hidden behind our own galactic disk. All those billions of stars, clouds of gas and dust that make up the plane of the Milky Way are sitting right in our line of sight, blocking our view like trying to see a candle flame through a brick wall. But X-ray telescopes changed the game. Unlike visible light, X-rays can punch through the dust and gas of the galactic disk, giving us a window into what's hiding on the other side. And with recent advances in X-ray telescope technology, astronomers have been able to detect thousands of galaxies in the region where the Great Attractor is supposed to be. Thousands of galaxies, hidden behind our own galaxy, now finally coming into view. But here's where it gets even more interesting. When scientists added up all that mass, all those thousands of detected galaxies, the numbers didn't work. There wasn't nearly enough mass there to generate the gravitational pull we've been observing. Something was still missing. Further analysis revealed something extraordinary. Yes, we are being pulled toward the Great Attractor, but the Great Attractor itself appears to be caught in the gravitational embrace of something even more massive sitting behind it. Something located 650 million light-years away, called the Shapley Supercluster, sometimes referred to as the Shapley Attractor. This structure is home to many thousands of galaxies packed densely together, with a combined mass of 10,000 trillion times that of our Sun. 10,000 trillion solar masses. And its gravitational reach is breathtaking. Everything within roughly 1 billion light-years is being pulled toward it. Our galaxy, our local group, our local supercluster, the Great Attractor itself. All of us are on a slow, cosmic journey toward the Shapley Supercluster. Now look in the opposite direction from the Shapley Supercluster, directly away from it, and you find something equally strange. A region of space that astronomers call the Dipole Repeller. This is an underdense region of space where, rather than galaxies being pulled inward, everything seems to be flowing away from it. It looks, from our perspective, as though something is actively pushing mass out of that region. But here's the important nuance. The Dipole Repeller probably isn't actually repelling anything. There's no mysterious anti-gravity force shooting galaxies away like a cosmic fire hose. What's most likely happening is that all the mass in the region surrounding it is being pulled toward denser areas, like the Shapley Supercluster, by ordinary gravity. And when all the mass drains away from a region like water flowing down a drain, what's left looks like a repeller, even though it's really just an emptying zone. Think of it like a crowd of people all rushing toward a concert on one side of a plaza. The plaza itself doesn't push them away, but it ends up empty because everything gravitational worth going to is somewhere else. That said, some scientists aren't entirely convinced by this explanation. A small number of researchers have argued that there may actually be some unknown repelling force operating in the Dipole Repeller, something we haven't identified or characterized yet. And honestly, that's not as crazy as it might sound. Because when it comes to understanding the universe at these scales, we are genuinely in the early days. We can observe the motion of galaxies. We can map dense galaxy clusters and measure the yawning emptiness of cosmic voids. We can trace the filamentary web of large-scale structure and watch the universe expand in real time. But the universe is an impossibly vast place. We can only see so far. Our instruments have limits. Our lifespans are a blink compared to the timescales on which cosmic structures evolve. The theories we have are our best current attempts to explain what we observe, and they're remarkably good. But I genuinely wouldn't be surprised if many of them are revised, refined, or even overturned, as new data flows in from the next generation of telescopes and observatories. Some people hear that and ask, what's the point? If our understanding is so incomplete, why bother? But I find it to be the opposite of discouraging. There is something deeply beautiful about the fact that human beings, small, fragile, short-lived creatures on a pale blue dot, are out here trying to map the structure of the cosmos, to understand why galaxies move the way they do, to locate ourselves within the unimaginable scale of everything that exists. That curiosity, that insatiable need to explore and understand, is one of the best things about us. It's what drives science forward, what pushes technology to new heights, and what keeps the story of humanity moving. So here we are, hurtling through space in ways most of us never think about. And on the grandest scales of our universe, something genuinely strange is going on. Scientists have come to realize that there simply isn't enough mass in the Shapley Supercluster to pull us toward it at the rate we actually observe. Roughly 50% of what's causing that motion is completely unaccounted for. Then in 2017, researchers discovered a possible source for the rest of that motion. And here's the twist. It's not something pulling us, it's something pushing. So let's dig into that. Let's explore the evidence for a region of space known as the Dipole Repeller, and try to understand how, in a universe that runs almost entirely on gravity, a force that only pulls things together, something out there can actually push us in the opposite direction. To make sense of all this, we need a little context. It took astronomers a surprisingly long time to even recognize that this large-scale motion was happening in the first place. Before scientists could understand that we were moving, they first had to build a map of the regions of space around us. And although humans have been mapping the stars since the very beginnings of civilization, thousands of years of looking up and drawing pictures, it wasn't until Edwin Hubble came along in 1924 that we proved, definitively, that there are stars in other galaxies outside the Milky Way. Before that landmark discovery, astronomers had noticed fuzzy little smudges of light scattered across the night sky, things we now know to be entire galaxies, each containing hundreds of billions of stars. But the prevailing wisdom at the time was that these were simply gas cloud spiral nebulae located within our own Milky Way. Nobody seriously entertained the idea that they existed beyond it. The universe, as far as anyone knew, was essentially just the Milky Way. What changed everything was Hubble's work on a particular type of star called a Cepheid variable. These are stars that brighten and dim in a very regular, predictable cycle, and, crucially, the length of that cycle is directly linked to how intrinsically luminous the star actually is. Think of it like a lighthouse with a built-in brightness dial. If you know how bright the light is supposed to be, and you can measure how bright it appears from where you're standing, you can calculate exactly how far away it is. Hubble spotted several of these Cepheid variables inside one of those fuzzy spiral structures, and used this relationship to calculate the distance with remarkable precision. The result stunned the scientific community. These objects were far, far beyond the boundaries of the Milky Way. An entirely new scale of the universe had just been revealed. After that, astronomers scrambled to catch up with this new reality. Galaxies were real, they existed beyond our own, and now the race was on to map their locations and distances across the cosmos. Hubble himself had been studying the Andromeda Galaxy, our closest large neighboring galaxy, but there were countless others waiting to be found and cataloged. By the 1970s, astronomers Stephen Gregory, Laird Thompson, and William Tift definitively proved that galaxies don't just drift around randomly, scattered through space like confetti. Instead, they clump together into enormous superclusters, vast filamentary and sheet-like structures, almost like a cosmic web, and these structures wrap around enormous bubbles of nearly empty space called voids. The first supercluster these researchers mapped was the Coma Supercluster, a structure spanning a region roughly 100 million light-years across. To put that into perspective, 1 light-year is about 9.5 trillion kilometers, so we're talking about a structure so colossal, it genuinely strains comprehension. And it's not an exception. A staggering 95% of all galaxies in the observable universe are found within these cosmic superstructures. Now here's something that might genuinely surprise you. It wasn't until 2014, nearly a century after Hubble's discovery of other galaxies, and about 40 years after the Coma Supercluster was first mapped, that our own home supercluster, the Laniakea Supercluster, was fully mapped. You might be scratching your head at that. Shouldn't it be easier to map the stuff right around us rather than distant structures? Why did it take so much longer to map our own cosmic neighborhood? The answer is that mapping the local regions of space immediately surrounding us is surprisingly, almost frustratingly, difficult. And the reason comes down to one very inconvenient obstacle: the Milky Way itself getting in the way of studying the Milky Way. Our galaxy is absolutely packed with gas and dust. These regions are so dense, so opaque, that light simply cannot penetrate them, at least not the kind of visible light our traditional optical telescopes rely on. Toward the center of the Milky Way, this problem gets so severe that scientists have given the region a rather dramatic name: the zone of avoidance. Very little usable light gets through it at all. And as we'll come back to shortly, the fact that we can't see clearly in this direction turns out to be deeply relevant to our story about the Dipole Repeller. By contrast, studying distant galaxies is almost straightforward by comparison. All you have to do is point your telescope at a single fixed point in the night sky, let it soak up the light coming from that direction, and analyze what you find. Mapping the space immediately around us, on the other hand, requires systematically surveying every single direction across the entire sky, a far more demanding task. But astronomers have been making real progress. By patiently studying thousands of galaxies in our galactic neighborhood, and by analyzing something called peculiar motion, the motion of galaxies relative to the cosmic microwave background radiation, which acts as a kind of universal reference frame that strips out the effect of the overall expansion of the universe, scientists have been able to identify which galaxies are gravitationally bound to each other and group them into superclusters. At the heart of our own Antlia Two supercluster sits a region known as the Great Attractor, an area somewhere between 150 and 250 million light-years away from us, toward which our entire local group of galaxies is slowly but steadily drifting. Somewhat frustratingly, the Great Attractor sits squarely within the zone of avoidance, which makes it genuinely tricky to get a clear picture of what's actually there. If that weren't complicated enough, the Antlia Two supercluster as a whole is itself moving, being drawn toward another enormous structure called the Shapley Supercluster, and dragging us along with it. At the core of the Shapley Supercluster lies the Shapley Attractor, believed to be extraordinarily dense in terms of mass. And, you probably saw this coming, this second attractor also sits in the zone of avoidance, making it equally hard to examine directly. Fortunately, as X-ray and infrared telescopes improved over the years, it became possible to peer through the obscuring dust and gas in new ways and take a much better look at both of these attractors. But this is precisely where the mystery begins to deepen. When researchers carefully tallied up the mass that could actually be detected in the Shapley supercluster, the numbers didn't add up. The mass that's there simply isn't massive enough to account for the rate at which we appear to be moving in that direction. Something was missing, about half the explanation gone. This discrepancy is what drove a team of researchers from the University of Hawaii to publish a groundbreaking paper in the journal Nature in an attempt to resolve it. The team consisted of Yehuda Hoffman, Daniel Pomered, R. Brent Tully, and Hélène Courtois. Together, they constructed a completely new kind of map of the local universe around us. Instead of simply plotting the positions of galaxies the way a conventional star chart would, they mapped the motions of those galaxies, building a picture of flow lines that show where everything around us is heading. Through careful mathematical analysis of these flow patterns, they were able to make inferences about where concentrations of mass must exist, even where they can't be seen directly. Their results were striking. As expected, a large amount of the matter in our local universe is flowing toward the Shapley supercluster. That much made sense. But they also found that a large amount of matter is consistently moving away from a completely different specific region of space, not toward anything in particular, just away from this one location. The team named this mysterious patch of space the Dipole Repeller. Taken together, the Dipole Repeller pushing from one side and the Shapley Attractor pulling from the other account for roughly 50% each of our overall motion through the cosmos, working in tandem like two ends of a cosmic seesaw. That's where the name comes from. A dipole, in physics, refers to a system with two opposing poles, in this case, one that attracts and one that repels. But this raises an immediate and genuinely puzzling question. How? Gravity, as far as we have ever observed, only pulls. It attracts mass toward mass. It doesn't push. So what could possibly exist in this region of space that produces something that functions like a repulsive force? Could it be some exotic collection of white holes, the theoretical opposite of black holes, objects we've explored before in other episodes? Could it be some undiscovered source of anti-gravity? Not quite. The answer, when you hear it, is both deeply counterintuitive and, in retrospect, elegantly simple. The dipole repeller is a void, a vast cosmic bubble roughly 100 million light-years across that contains very little. So how does nothing actually push you? The answer is that what we're really dealing with here is more of a pseudo-force than a genuine push in the traditional sense. Think of it this way. Imagine a universe where galaxies are perfectly and evenly spaced in every direction around you. The gravity from galaxies above you pulls you upward. The gravity from galaxies below pulls you downward. Galaxies to your left pull you left. Galaxies to your right pull you right. All of these forces are roughly equal, so they all cancel each other out. You float in perfect equilibrium, going absolutely nowhere. You're like a tug-of-war rope when both teams are equally matched. Now, what happens if you remove all the galaxies from one of those directions? What if, instead of galaxies on your left, there's just a void? Suddenly, the balance is broken. The pull from your right still acts on you, but there's nothing on the left to counteract it. The net result is that you drift to the right, away from the void, as if the void itself were literally pushing you away. Everything in the neighborhood of a void will experience this same effect, drifting away from the empty region, which makes the void look like it has some kind of repulsive gravitational force. But it doesn't, not really. It's an optical illusion of gravity. The void isn't pushing. The rest of the universe is just pulling more from the other side. But wait, there's actually a second mechanism that might be working alongside this pseudo-force, and it has to do with the expansion of the universe itself. The universe is expanding, and that expansion shows no signs of slowing down. If anything, it appears to be accelerating. Now, gravity works against this expansion. In regions packed with matter, dense galaxy clusters and superclusters, gravity fights back against the expansion and keeps things relatively contained. Stars and galaxies are being pulled toward each other even as space tries to push them apart. But in a void, there's almost no matter, which means there's almost no gravity to put the brakes on expansion. The result? Void regions literally swell and grow faster than their matter-packed counterparts. The fabric of space itself inflates more rapidly in these empty zones, and that physical swelling of the void acts as yet another kind of push on anything near its edges. It's a subtler mechanism, but it works in the same direction as the pseudo-force, both of them conspiring to drive matter away from the void. Now, since the dipole repeller was first proposed back in 2017, the scientific conversation around it hasn't exactly exploded, but it hasn't gone away either. This is still very much an active and expanding field of research. There's genuine debate among astronomers about whether the dipole repeller is truly there in the way the researchers describe, and about just how much influence it actually has on the Milky Way's motion through the cosmos. Part of the difficulty is purely practical. The region in question lies behind the plane of our own Milky Way galaxy, and the dense disk of stars, gas, and dust in our galaxy obscures our view like a thick fog rolling in front of a lighthouse. It's hard to see through it. On top of that, there's a fundamental conceptual challenge. You're trying to detect and study the absence of something rather than the presence of something. Spotting a void is, in a very real sense, much harder than spotting a galaxy. You're looking for what isn't there, and that requires an extraordinary level of precision and sensitivity. Researcher Yehuda Hoffman and his colleagues, including Tully and the rest of the team, remain hopeful. They're looking forward to the next generation of ultra-sensitive sky surveys, instruments capable of scanning across multiple wavelengths of light, from radio waves to infrared to optical, that could help map out even the sparse few galaxies that do exist within this void, and confirm whether the structure they've identified truly sits where they think it does. So there we have it. We are constantly moving through space, But then again, so is the science of space itself. Every new galaxy we discover, every measurement of redshift, every data point about how fast something is moving and in which direction, adds another piece to this enormous cosmic puzzle. It's genuinely remarkable to consider that not all of the Milky Way's motion is driven by the gravitational pull of something massive and visible. Some of it might be driven by the gravitational absence of something, a vast, dark emptiness pushing us along like an invisible hand. Now let's talk about something you may have come across before. Boötes Void. You might have heard it described as one of the largest known voids in the observable universe. But what does that actually mean? And do you really know what it looks like? First things first, if you search for Boötes Void online, one particular image tends to pop up constantly. It shows what appears to be an inky black circular patch against a starry background, like a hole punched through the night sky. That image is striking, and it certainly looks like a void in space. But here's the thing, that's not Boötes Void at all. That image is actually of something called Barnard 68, a molecular cloud, essentially a dense blob of gas and interstellar dust sitting relatively close to us in our own galaxy. The dust in Barnard 68 is so thick that it absorbs all the light from the stars behind it, making it look like an empty hole. It's a bit like looking at a dark storm cloud and thinking you're looking at clear sky on the other side. It's a perfectly understandable mix-up, but it's worth clearing up. So what is Boötes Void really? To understand it, we need to zoom out, way out, and get a feel for the scale of the universe in layers. Start close to home. Within Earth's atmosphere and just outside it, space might feel vast, but it's actually quite populated on an astronomical scale. You've got the moon, the planets, asteroids, comets, and the sun, all of which you can measure in kilometers or miles. These are distances a human brain can sort of comprehend. Step out beyond our solar system and distances stretch dramatically. Now we measure in light years, and 1 light year is approximately 9.46 trillion kilometers. That's the distance light travels in a full year, moving at about 300,000 kilometers per second. At this scale, we begin to see that our cosmic neighborhood is filled with stars. All the stars you can see in the night sky, and hundreds of billions you can't, are part of the Milky Way galaxy, a sweeping spiral structure roughly 150,000 light-years from one edge to the other. Zoom out further and you find other galaxies. The nearest large one is the Andromeda galaxy, sitting about 2 million light-years away from us. Beyond Andromeda lies a collection of galaxies that includes the Milky Way, a gravitationally bound group that astronomers call the local group. Zoom out further still and something remarkable becomes apparent. Galaxies are not randomly scattered. They cluster together into groups, and those groups align into long threads and sheets called filaments, which connect into a vast web, the cosmic web. It's one of the most breathtaking structures in all of nature. Between these filaments and galaxy clusters are regions where very little exists. On the smaller scale, these gaps are called voids, perhaps just tens of millions of light-years across. At the largest scale, they become supervoids. Boötes Void is one of the biggest supervoids we know of. It spans approximately 330 million light-years from one side to the other. To put that in perspective, a typical region of space that size would be expected to contain something in the neighborhood of 2,000 galaxies. Boötes Void contains a mere handful. About 60 galaxies have been detected there so far, arranged in a thin, lonely filament threading through the emptiness. And that sparseness is almost incomprehensible. Astronomers have calculated that if our own Milky Way were located somewhere in the middle of Boötes Void, we would not have discovered the existence of other galaxies until sometime in the 1960s, not because of technological limitations, but simply because the nearest neighboring galaxy would have been so impossibly far away that only the most advanced mid-20th century instruments could have picked up its faint signal. Imagine living your entire history of civilization under a night sky that offered no clue, none at all, that other galaxies existed beyond your own. That is the kind of isolation Boötes Void represents. So that's what Boötes Void truly is, not a dark cloud in our galaxy, not an artistic rendering, but a genuinely, almost incomprehensibly empty region of space, hundreds of millions of light-years across, containing a small scattering of extraordinarily lonely galaxies drifting through a vast cosmic silence.